Hi there, Mr. Chan here for Algebra 2. About to start a new chapter, topic 6. This particular section is 6-1, key features of exponential functions. Please grab your note takers and turn to page 139, and let's get started. Here we go. The key to this topic is called exponential functions. We're going to compare this concept, these functions, to a couple of things we already know about already. Let's take a look at the explore and reason. Margaret investigates three functions: y equals 3x, y equals x to the third, and y equals 3 to the x. She is interested in the differences and ratios between consecutive y values. Here's the table she started for y equals 3x. Very good. So y equals 3x, we know, is a linear function from Algebra 1. It's a line. And if you look at this table here, she's already found the differences between each value in the domain. And what she's finding, think about this, pretend this is a table of value that you might have seen in Algebra 1. The difference between one y value to the next is simply 3, right? Rise over run. And when we found that, it's basically taking the current value and subtracting the previous value. That, of course, is called the common difference that you learned about a while back. Let's take a look at the ratio between the y values. When we do a ratio, you notice that they are dividing the current by the previous. So let me remind you of what we did with differences. This was, before I talk about the ratio, common difference was current minus previous. That's true because it's linear. But if you check the ratio, ratio means division, current divided by the previous value. We see that there is no common ratio. That's a characteristic of something that's linear. Okay? Pretty straightforward there. Let's go ahead and take a look at all three functions together. Create tables like Margaret's for all three functions and fill in more rows. We're going to explore those three functions and compare them together. Here we go. So the first column will be my domain. Let's just pick some x values here, 1, 2, 3, and 4. We've already created, we're just going to recopy what we had for the linear in the second column, y equals 3x. This is the linear function. And I'll just copy those numbers up there in the previous table, 3, 6, 9, 12. And that, of course, will graph a linear function. The second function is called a cubic function. This is your typical polynomial, right? In this case, we'll make it green. This is cubic, meaning to the third power. Let's just visualize that number. Let's put in the domain 1, 2, 3, and 4. 1 to the third power is 1. 2 to the third power, let's see, 2 times 2 times 2 is 8. 3 to the third power is 3 times 3 times 3 is 27. And 4 to the third power is 4 times 4 times 4 is 64. You can always check that with your calculator, okay? How about the last function here? This is what we're going to explore with this chapter, this topic. This is called an exponential function. In fact, it's called exponential growth that you remember from Algebra 1. So if we put in 3 to the first, 3 to the second, meaning 3 squared is 9, 3 to the third is 3 times 3 times 3 is 27, and 3 to the fourth is 81. Looking for a pattern here, we know right away that the third and the fourth columns are not linear. 1 to 8, 8 to 27. There's really not much going on here in terms of linear increases. So we have to look at, are we multiplying by something? It's kind of interesting because with the third column, the cubic function, yes, we multiply by 8. That's true for the first pair of numbers. But how do we get from 8 to 27? We don't know. So that's based off of the actual domain value when you put it into the function. The last column here is kind of interesting. We are multiplying by 3. So that's kind of interesting because the base is 3. Okay, that's why we call that exponential growth. All right, next question. Which functions have a constant difference between consecutive y values, constant ratio? So let's look at like the constant difference we talked about briefly. That, of course, is what we explored earlier. The linear function has a common difference, meaning we're adding 3 each time. And when you're adding 3 each time for every x value, it becomes a linear function. The one that has a common ratio is the last one, which is what we're exploring in this particular chapter. Common ratio, they use the letter R, and in this case, it's times 3. Now, technically, think about that. We are multiplying and creating a 300% increase here, so to speak. There it is. That's your base value. This is an exponential function. Gets pretty big fast, doesn't it? Next question. Which of these 3 functions will have y values that increase the fastest as x increases y? Well, obviously, let's go ahead and explore these because besides the table, we can explore using decimals or a graphing calculator. Let's do that right now. Switch over to decimals. Dun, dun, dun. All right, here we go. I have for you, there's my linear function, y equals 3x. Next one is y equals x to the third. That's a cubic function. Notice that the relationship there between the red line and the cubic function changes on us. The cubic function is actually below the red function until it hits a certain x value. Then it launches really fast, doesn't it? The blue one. But what if we turn on the exponential function, that green one? Look at that. That green one wins all. If I zoom out, it's kind of hard to see, and I wish oh, there it is. See how the green is ahead of the blue right there? Okay, it's higher than the blue one. It's hard to see, very hard to see. So it's the exponential that wins in the end of the day when your x values get really, really large. But here are the 3 functions relative to each other near the origin. Let's jot that down in our note taker. Definitely the exponential growth function wins. Right? What did we do? We looked at the graphs. And you can look at the tables too. If you have your graphing calculator, and as your x values increase, you can see the y values really, really shoot up for that. But think about the actual functions and so on. You got your cubic, your quartic, your quintic, and so on and so forth. It is getting bigger, but not as big as this one. 3 to the x, 4 to the x, 5 to the x. Those get really, really big fast. So the winner is, of course, this guy. Okay. So what does that mean for this chapter? You've seen a little bit of this in Algebra 1 when you talk about exponential growth and decay. We're just exploring more and more of it in this chapter. Here, we have representative where f of x is exponential growth, okay? So we have b to the x versus the other one is a polynomial, x to the b. That's what it comes down to. Which one has more growth? The base for this chapter is right there, whereas the base is up here for your polynomial. It's not really a base, but let's make note of that. Hands down, the exponential function wins at the end of the day. It gets bigger, faster, really, really fast. B is greater than 1. When a B is greater than 1, that means we will have exponential growth. Now, the opposite of growth is actually called decay. You may remember from Algebra 1. Decay works if the base is between 0 and 1. So make that little note off to the side here. We'll explore that some other time. So that's something else, okay? Don't worry about it right now. All right. Let's go to the next page. So like anything else, when we come across a new type of a function, we have a relationship where graphing is related to A, H's, and K's again. Here we go. A is your initial value. It's also your vertical stretch, shrink, and reflection value, times B to the X minus H plus K. All those things apply when it comes to graphing. It's pretty amazing how they're all linked together so easily, right? Instead of doing one here on the note taker, I'm going to actually throw in a very simple one off to the left here, just to say we explored something very basic first. So off to the left, let's write down an easy one. Example, f of x equals 2 to the x power. All right. Let's see. We're going to go ahead and pick some values for it. The easiest ones to pick are 0 and 1. Let's plug it in. 2 to the 0 power is 1. 2 to the first is 2. So ladies and gentlemen, this particular parent graph, when you graph it, will look like this. Zero comma 1, great. And 1 comma 2. In fact, when you graph this one on Desmos, you'll see that it looks like it's like this. Whoa! Looks like a plane taking off, doesn't it? Here, your B value happens to be 2. That's your base. And because it's bigger than 1, this is considered growth. Okay? There's an actual A value. It's kind of invisible right now. The A value is 1. Okay? Just want to make clear there. And this particular graph looks like a plane taking off from left to right. In fact, it looks like it's on the runway, but it's kind of weird. It'll never hit the x-axis. There's a name for that guy. This x-axis is called the horizontal asymptote. There's a name for that. It helps guide the graph. The word is asymptote. We mentioned this before in Algebra 1. The formula for it is y equals 0. It's a horizontal line. All right? So just to recap, the 2 points for this parent graph, of course, are 0, 1, and 1, 2. Just to remind you of that. And depending on the base you have, sometimes that 1, 2 is technically 1b, the base generically speaking. So whatever base you have, the 2 will replace by that base number. We do need to briefly talk about the domain and range. Take a look at the x's in this particular case. No matter what you plug into the equation, it will work. So the domain is all real numbers. The range is kind of interesting for this parent graph. All my y values are positive. So that means it's going to be greater than 0. Some other things that we look for in terms of characteristics with this graph, there is a y-intercept. It does cross the y-axis at 1. This is when x equal to 0. Just a little reminder from back then. One last thing, I know this is a lot for one little problem. What if they ask you for end behavior? End behavior is not the same as is it increasing or decreasing. Increasing, decreasing goes from left to right. Now, obviously, if they ask whether this function is increasing or decreasing, a plane taking off is definitely increasing from left to right. But end behavior is from the middle of the graph. End means the left end and the right end. So this is definitely different from increasing or decreasing. End is from the middle. So if I go from the middle to the left, the graph is approaching a certain number. Is it going way down to negative infinity, or is it going way up to positive infinity? Or in this case, going way left, it's approaching the horizontal asymptote. Y equals 0. Isn't that interesting? When it's going to the right, it's shooting up, 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 up into the sky. We call that as approaching positive infinity because it's going way, way up. The verbiage, okay, is going to come back and haunt you on the final and on SATs and ACTs. Looks like this. They'll ask you about the end behavior. You have to fill in this blank. As your x value approaches left, see that negative infinity? Negative infinity means left. The y value approaches what? Would be a blank. In this case, it approaches 0. That's the actual equation for the horizontal asymptote, or the x-axis. Sometimes it approaches a number. In this case, it's 0. See right there? That, going to the left, the y value approaches 0, but it will never reach it. It'll never hit 0, though. It's approaching it, okay? So keep that in mind. This is a calculus concept, actually, for certain types of graphs. Let's go the other way. So that was yellow, right? As x approaches negative infinity, what's happening? It's going to 0 from the middle. Let's go the other way. As my domain goes to the right, positive infinity, the y value approaches what is the question? So here I'm going to the right, and I'm using green. Whoops, wrong color. Green. I'm going to the right. This time it's going way up there. Woo! This is going to be positive infinity. It's going way, way up. All right. So this is something that is new for most of you, the idea of end behavior, and it's from the middle. Okay. All right. Any questions? You guys ready for the actual problem on here? So switching to Desmos here, you can see that that graph right there is an exponential growth function from left to right. And then we just got that a few seconds ago. The actual problem on your note taker looks like this one right there. Oh, that's kind of interesting. This is in your note taker, f of x equals 4 times 0.5 to the x power. That 0.5 changes things. 0.5 is not a number greater than 1. Greater than 1, like the previous one, is going up from left to right. Less than 1 is going down. This is called an exponential decay function. See the difference? It's like a plane landing from left to right. So let's make note of that in our note taker. All right, here we go. I'm going to copy that onto here from my Desmos or graphing calculator. Pick a couple of points here. I'm going to pick 0, 1 again. So let's follow along. I'm going to plug it into here. Okay. 0.5 to the 0 power is 1. 4 times 1 is 4. Okay. 0.5 to the first power is 0.5. 0.5 times 4 is 2. I'm going to plot those 2 points, 0, 4 and 1, 2. And what you saw from Desmos a few moments ago, it's a graph that looks like this. It's the decay function going from left to right. There's a horizontal asymptote still there that helps guide it, but that graph will never hit the x-axis. They'll never hit it. There's no way that this equation will ever equal 0 or is negative, right? There's no way. All right, so that's your horizontal asymptote. And we do sometimes shorthand it as HA, horizontal asymptote. In this case, it's still the y equals 0 equation or the x-axis, okay? So kind of interesting, some observations here. Some observations that the value of A happens to be 4. That's a vertical stretch. You remember from your transformations, vertical stretch. The 0.5 is your B value. That is definitely between 0 and 1, which means this is an exponential decay function. All right, so that's what is going on in this particular graph. We do need to talk about the domain and range. Let's do that. The domain, of course, it works for all xi, so it's all real numbers. Great. The range is kind of interesting. Even though it's decaying, the graph is still above the y-axis, okay? So all your y values are still positive. There's a common mistake that happens when kids see graphs dropping from left to right. They think it's less than. It is less than, but is there a way to describe all the values relative to a number on the y-axis? That number is, of course, 0. Where are all the y values? Well, they're above 0 still, even though the graph is going downward, but it'll never hit 0 or go below 0. It's kind of a weird way of looking at where things are located, right? So the range is still greater than 0, okay? In this case, my y-intercept is y equals 4. We do need to mention that because they asked for that. See, they asked for any intercepts. So in this case, we do have a y-intercept. And that y value is 4. This is when x equals 0. One more thing they asked for are the end behavior again. So let's talk about that. End behavior. Okay, so we're just going to have to get used to the verbiage. As x goes left, what's happening to the function? As I go left of the graph, it's going upwards. So here, my y value is approaching positive infinity. Okay, it's going up from the middle. As x go to the right, my value is, dropping and it's approaching 0. Okay, that's a calculus concept again. It's approaching the x-axis. All right, that takes care of number 1. This is a lot to absorb. Let me know if you have any questions. We can go back and go over some of these concepts if you want to in class. All right, let's move on to number 2. Here we go. How do the asymptote and intercept of the given function compare to the asymptote and intercept of the function 5 to the x? So this is kind of interesting. Don't forget our parent function, a times b to the x minus h plus k. Our parent graph in this case is 5 to the x power. Great. 5 to the x is pretty easy to create some points for, if you think about it. They are, pick 0, 1, 5 to the 0 is 1, 5 to the first is 5. Those are your points that you will plot for the parent graph. 1, 2, 3, 4, 5. So here's your parent graph right there. Okay, it's an exponential growth function like that. Right. Oh, let's take a look at A. A, we have a +3. Now, +3, is that H or K? If you look at over here, it's definitely H right there. And you got to think backwards, right? So in this case, H is -3. H reminds me of the horizon, H, horizon. This is going to move my parent graph left. One, 2, 3, 4, 5. 1, 2, 3, 4, 5. Always throw in your parent graph first. 0, 1, 1, 5 is your parent graph. And I'm going to move those 2 black dots 3 spaces to the left. 1, 2, 3. 1, 2, 3. Note that the horizontal asymptote doesn't get moved. It basically stays the same. It technically is moved to the left, but it stays the same. Oops. Kind of messed that up a little bit. There it is. It's 5 to the x plus 3. Okay? Very good. That's your g of x function. What do they ask for? Oh, compare. Very good. The horizontal asymptote stays the same. Y equals 0 still. Stays the same because it's the k value. K value is 0, okay, HK. And the y-intercept, they're looking for? Great, let's figure that out. Where does this part cross the y-axis? It's kind of hard to see. So let's look for that. Y-intercept. You want to set x equal to 0 from the original function. So here, 5 to the 0 plus 3. That equals to 5 to the 3rd power. Holy cow, 5 times 5 times 5 is 125. You'd have to zoom way out there to see that this function will cross the y-axis at 125. Pretty crazy, huh? Way up there, way up there, way up there. I wonder if Desmos works that way or not. Let's take a look at Desmos. Oh, I have it right here, yay. So this is right, this is the function that's been shifted to the left from the parent function. I'm going to zoom out. Let's see how far we can go here. Zoom, 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 zoom. Oh, let's see. Zoom into that 150 right there. Is that considered a y-intercept? It's hard to click. Really hard to click, so. Oh. Oh, I'm sorry, 125. I don't know why I said 150. Dun, 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 dun. There it is, ladies and gentlemen. 0, 125. Yay. So that, using a graph to explore, that's my y-intercept there. Very good. Very, very good. Okay, that takes care of that one. Let's go back and do the next problem. Okay, so here I have a negative number. Kind of weird, huh? Ooh, if you look at my original problem here, my thing, I don't have anything with a coefficient right there in front of x. So I have to play a little trick on you guys a little bit. I'm going to apply the negative exponent property there. I'm going to rewrite that problem, okay? H of x equals to 1 over 5 to the x. Negative exponents, so you reciprocate the problem, okay? And then I'm going to do another little twist to this thing. I'm going to call this 1/5 to the x power. See what I just did there? I'm like unapply the exponent property, because 1 to the x doesn't do anything, but 5 to the x on the bottom is right there. So this is kind of interesting. We've just uncovered your base. Your base is 1/5. This is decay, ladies and gentlemen. This is your b value. Your b value is between 0 and 1. Definitely decay, all right? Let's draw it. Kind of a crazy twist on everything, isn't it? So let's put in our parent graph again. 1, 2, 3, 4, 5. And I'll be picking some values here for you. 0 and 1. 1/5 to the 0 power is 1. 1/5 to the first is 1/5. So when I plot this relative to the parent graph, this is your parent graph, something interesting happens when you compare these two graphs from one situation to the other one. 0, 1, 1, 1/5. When you plot this, you'll get a mirror image, ladies and gentlemen. This is your decay function. Very cool. The horizontal asymptote stays the same. Nothing changes there because there's no k value to move it up or down. Okay, so it stays the same. So I'll write that down. And my y-intercept really is the same as the original when you set x equal to 0. And it's already in the table. Here, it's y equals 1, all right? Whereas earlier is 125, this is 1 right here. Does Desmos agree with us? Let's take a look. Desmos. Turn that off and turn that. Oh, there it is, yay. It's a decay function, okay? Very good. Back to the notes. I'm going to throw in one more for example 2, okay? Let's go off to the left here. We haven't played with any k values, so I feel like we need to. This is going to be example C. Let's graph 5 to the x minus 4. Bam, there's my k value. My k value in this case is -4, which means that it's going to go down. Let's graph it. I'm going to put in the parent function again. 0, 1, 1, 5. That's your parent function. And this time we will witness the horizontal asymptote actually moving along with the graph itself. Those two black dots are going to go down 4. 1, 2, 3, 4. Boom. 1, 2, 3, 4 right there. Also, the asymptote gets moved down 4 places too. 1, 2, 3, 4 right here. So here's the graph. Very good. Everything shifts down, including the horizontal asymptote. The horizontal asymptote, it gets moved to -4. That's the k value that I mentioned before. Yay. And the y-intercept, interesting, is right here. Visually. When you set x equal to 0, literally you can do the math. 5 to the 0 minus 4 and verify it. 5 to the 0 is 1. 1 minus 4 is -3. That's correct. That's your -3 value right there. Okay? Woo! Crazy. So the habits of mind, if there are any questions, let me know at the bottom here. What kinds of transformations will affect the asymptote or the intercepts of an exponential function? Intercepts are affected by A's, H's, and K's. The asymptote, which is a horizontal one, is affected by your K value only, which are the vertical shifts, up and down. Okay? All right. Ooh, let's jump to the next page. Here we go. Yeah, this is a brand new parent graph that we're going to exploring a lot of stuff with, right? There's a lot going on here. Now, in Algebra 1, and also in this course before, we talked about how things have, in the real world, whether they grow or decay. Taking that function, y equals a times b to the x, we can focus in on whether something's growing or decaying by how the rate affects it. The base is based off of whether you have positive rate growth or negative rate growth. So you might see the formula like this: a times 1 plus r to the t power, t is time, or a times 1 minus r to the t power. And these rates are percentages, right? Okay? When you add something, you produce growth. When you subtract something, you produce something, decay. Think about the base. Okay? We're not doing anything new. We're just referring to it relative to the percentages. So let's take a look at our opener here for number 3 and read the problem a little bit. A factory purchased a 3D printer in 2010. The value of the printer is modeled by the function f of x equals to 30 times 0.93 to the x, where x is the number of years since 2010. Very good. So whether you use t's or x's is just basically time. What is the value of the printer after 10 years? So here, 10 is going to be placed into the equation where x is, okay? So let's throw that in. Function notation wise, it's going to be f of 10 equals to 30 times 0.93 to the 10 power. Now, all you have to do is punch that in your calculator. When you do, you'll get 14.5. Oh, that's really dropped. Why did it drop? Because your initial value was 30. Okay, remember? Oh, I didn't mention that, did I? Sorry about that. A is the initial value. My bad. That's where you start, okay? Your initial value. This is when x or t is equal to 0. When it starts. Our starting value was 30. It could be $30,000. I don't know, $100, $30 million. They're not really specific about that. But it drops to 14.5. That definitely is a drop. Second question. Does the printer lose more of its value in the first 10 years or in the second 10 years? Interesting. So we already got the first 10. Let's take a look at the value after 20 years. Now, of course, you need a calculator to punch in this equation, 30 times 0.93. And by the way, 0.93 literally means after 1 year, its value drops to 93% of itself. Then the second year will be 93% of its previous year, 93 of 93%. It's a percentage of a percentage. That's how the equation's working. So when we punch in 20 years on our graphing calculator or regular scientific calculator, we'll get 7.0. Wow. That's kind of a thing. So let's see how much the value loses from the first 2 years to the second 2 years, okay? Let's take a look at what's going on here. Let's compare. So the first 10 years are the years 2010 to 2020. 2010, the value of the printer was $30,000 or $30 million, doesn't matter, minus this number, 14.5, how much it's worth. When you subtract those, 30 minus 14.5 is 15.5 loss. Let's do the next 10 years, 2020 to 2030. 2020, the value is 14.5 from part A, minus down to 7.0 in part B. When I subtract those, I get 7.5 loss. So clearly it loses the most value the first 10 years because the second 10 years is a lot less. Lost more the first 10 years. A lot more. Okay. Very good. Interesting. Don't let these word problems scare you. They follow the same basic formula. Initial value times growth or decay and bring it to a time or X variable kind of a thing. Oh, let's take a look at number 4. 220 hawks. See, notice this is the formula right there. Were released into the region in 2016. The function f of x equals 220 times 1.05. Interesting. Isn't that bigger than 1, everybody? That's definitely growth. In fact, that is 5% growth. 0.05 as a decimal is 5% when you move it 2 spaces to the right. In fact, it's 105%. Can be used to model the number of red-tailed hawks in the region X years after 2016. Is the population increasing or decreasing? Well, obviously 1.05, the base, when you convert it into 2 separate decimals, this means it's 105%. So this is definitely growth, which means it's increasing. No mystery there. There really is not a lot of mystery in math. The formulas look a little scary, but you just have to break it down. Second question, in what year will the number of hawks reach 280? So this is more of a guesstimate. We haven't learned how to solve this yet on the graphing calculator. I'm sorry, by algebra. So sometimes it might be ideal to graph this on the calculator. All right. So when or how long will it take for it to hit 280 hawks? So you replace the y value with 280. And what you want to do is you want to use a graphing calculator. And you want to trace it. I'm going to demonstrate that in class. You're going to have to do it on your own at home, okay? Use a trace function on the graphing calculator and just go to the right. And what will happen is that when you get near X is about 5 years, it will approach the number 280. 5 years after 2016 would be in the year 2021. I don't have that ability on here to show you that progression, but use a trace function on your graphing calculator. All right. I'm going to skip the habits of mind right here. Next question, number 5. Here we go. How are we doing out there? Yeah. Very different, isn't it? Okay. So number 5 is referring to an example in the book, and I need to explain that. Let's go off to the left here and create our own. From the textbook. It's actually in the textbook. Example 5 says we have a sculpture. And this sculpture has a function that refers to how much its value increases. Now, I say increases, I kind of jumped the gun a little bit because of the multiplier was 1.075 to the x power. Question, in 5 years, which piece has a higher rate of change? They're referring to a sculpture and a painting. Rate of change is slope. I haven't given you the information for the painting yet. Hold on a second. The sculpture is the function right there that I just wrote down. The painting is an actual graph. So I kind of jumped the gun in terms of asking the question. Here's the graph itself. And it looks like this. And there are a couple of points in the picture. They are 0, 40, and 5, 64.4. The horizontal asymptote is referring to time, of course. And the vertical asymptote is the value of the painting in thousands of dollars. Very good. So when you look at this, we need to figure out which one has a higher rate of change. Now, rate of change is basically slope. In the painting, we've already given a couple of points. All we have to do is figure that out in a moment. But before we do that, let's go ahead and find the slope for the sculpture first. Let's do that, okay? So we're going to take the equation and find the slope. Now, which points do I pick? Look at the painting. I have 0 and 5 already given to me. We are dealing with 5 years, right? So I got to plug in the number 0 into the sculpture's function. So let's put that information in right now. There we go. F of 0's first. That equals to 50 times 1.075 to the 0 power. This equals to, let's see, 0, that's $150,000. Okay, great. We're just going to assume it's $50,000. Let's put in the function 5. 50 times 1.075 to the 5 years. You punch that all into the calculator, you'll get 71.78. Okay? Trust me on that one. For the slope, remember slope is y2 minus y1 divided by x2 minus x1, okay? So think of this way. This is x1, y1, x2, y2. Let's put in that formula. The formula, I'll write it down for you guys, no big deal. y2 minus y1 over x2 minus x1. This equals to, let's put the numbers in. 71.78 minus 50 over 5 minus 0. When you put that all in, your slope is 4.356. That's $4,356 per year. That's one way of looking at it, okay? Let's look at the painting values slope. Okay, here we go. The coordinate points are already there, so that's cool. So this equals to, and I'll do this, x1, y1, x2, y2, and put it into that formula right there. 64.4 minus 40 divided by 5 minus 0. This equals to approximately 4.88. So this is kind of interesting. The bigger value refers to a bigger slope, meaning the painting has a higher rate. Okay? So yay, there's your answer. The painting has a higher value. All right, next question. Habits of mind. For two functions, f of x equals b to the x and g of x equals b to the x plus n, where n is greater than 0, is it possible that the two graphs will intersect. This is very generic. E to the x is a function that goes to 0, 1, and 1b, right? The base is b. So generically speaking, the function, let's use orange, is right here. What happens if you throw in an n value? That n is positive. You know, like x plus 3 or x plus 5 or x plus 9. Now, if it's plus 9 plus 3 plus 9, what's going to happen is that it's going to be shifting, okay? It's shifting to the left because the n value is the h value, which will be negative, right? Remember the formula is x minus h. If my h value is positive, I'm sorry, if my n value is positive, I have to think opposite of plus n, I got to think minus n. So when it's negative, it's going to shift left. Looking at this graph here, if I shift to the left anywhere, those graphs will never cross. Make sense? Okay. If I go left, those will never cross. So is there a point of intersection? The answer is no. They'll never cross. All right, let's jump to the last page. Dun, 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 dun. All right, just a reminder, a times b to the x minus h plus k. Number 5, graph the function f of x equals 4 times 3 to the x. Identify the domain, range, intersect, asymptote, and describe the end behavior. Okay, a whole slew of stuff there. The way they wrote that function looks kind of funny. That time symbol looks kind of funny. That looks like an x. This is multiplication, okay? All right. So, great. Let's pick some x values here. 0 and 1. Our go-to domain. 3 to the 0 power is 1. 1 times 4 is 4. Great. 3 to the first is 3. 3 times 4 is 12. It looks like I'm going to have to scale this a little bit for myself. I'm going to use axes like this and go by 2s. Okay, let's go by 2s. 0, 4. And 1, 12. 4, 8, 12 up here. Okay, great. And there's your graph. The domain is all real numbers. That's easy. We've done that a few times. The range, it looks like everything's above the x-axis. It's going upwards. So my range is y is greater than, just greater than 0. Nice. The y-intercept is next. Looks like it's right there. Oh yeah, there it is. 0, 4, literally, it's staring at you right there. 0, 4, that's my y-intercept. Horizontal asymptotes next. Well, I don't have any k value here to shift it up or down, so the horizontal asymptote stays the same. Y equals 0. Great. And behaviors last. To kind of get used to this notation. From the middle now, going left, looks like my y value is approaching 0. As x approaches left, my y value approaches, whoops, wrong color. Approaches 0, nice. As we're going to the right, positive infinity is right, remember that. My y value goes forever up, which means positive infinity. Yay! Very good. Not too bad. All right, number 6. The exponential function f of x equals to 2500 times 0.4x models the amount of money in Zachary's savings account over the last 10 years. Is Zachary's account balance increasing or decreasing? Write the base in terms of the rate of growth or decay. Now this is kind of shocking a little bit. 0.4 is definitely a number less than 1, right? This is definitely decay. What's going on? Why is Zachary losing money? Is it like an investment account where he's losing money with certain stocks? Sounds like it, doesn't it? So this is decreasing, definitely. It's losing 60%, right? 40% is 60% loss there. So the base is literally, when you convert to 0.4, it becomes 0.42 to the right. This is a 40% growth, also known as 60% decay. So that's kind of shocking. And in this case, it's 1 minus r is your expression. Number 7. Describe how the graph of g of x equals to 4 times 0.5 to the x minus 3 compares to the other graph of 4 times 0.5 to the x. That minus 3 is very subtle, okay? Just remember, compared to this, it's your h value. H value is positive 3. If it's positive, which means it's going to be shifting to the right. That's it. All right, any questions about number 7? All right, number 8, we're definitely going to use a graphing calculator for. It's kind of cool to use that kind of technology. 2 trucks were purchased by a landscaping company in 2016. Their values are modeled by the functions f of x equals to 35 times 0.85 to the x and 46 times 0.75x, where x is the number of years since 2016. Which function models the truck that is worth the most after 5 years? So we can use a graphing calculator here to graph that in a second. Let's go ahead and punch in the number 5 for both of them, okay? F of 5 for the first truck is equal to 35 times 0.85. They both lose value. Anytime you buy a new car, you lose value. If you punch that into the graphing calculator, you'll get $15.5 thousand for the first truck. Looks like the first truck costed $35,000, but it's losing about what is that, 15% loss? See how 15 and 85 add up to 100%, okay? The second truck, after 5 years, is worth how much? It costs more, but it looks like it loses more over time. Look at that, 0.75. It loses 25% decay. That's kind of interesting. Anytime you're buying a truck, you gotta look into the reputation, the reliability, punch that all in. Oh my gosh, the most expensive truck loses more over time. Therefore, it's down to $10,900, not a lot. Now, what I'm gonna do now is I'm gonna use a graphing calculator to see where they are equal, okay? Just to see that comparison. All right, here we go. Decimals, here we go. Oh, I forgot about all these other ones. Here's the first truck. Oh, interesting. It's decaying. The first truck's $35,000. You guys see that 35 right there? Right there, 35, 0 years, $35 off of the lot. Second one, $46,000. Right about there. There it is, 0.46. And this is the point right here that they both equal in value. That's kind of interesting. See how they intersect each other? They intersect each other right there, it's approximately 2.183 years where they equal each other in value. That's really cool. So let's translate that onto the graph. And we're done. I just wanted to see a little extra information. It's kind of cool. 2.2. So we have 5 years and about 2.2 years. The graphs look like this. Whoops, that was really bad. Sorry about that. All right, there they are. This is g of x, and this is f of x. Yay. Well, thank you very much. That was an interesting lesson on exponential growth and decay functions. Let me know if you have any questions. Thank you very much. Have a good day. Bye-bye.